Hey guys, I'm your friend Humayun Malik and today we are going to discuss nuclear cross-section. But before going to our discussion, just in order to get comfortable, I want to tell you guys that I had spent a lot of time on this video. And in the end, all I want you guys to like my video, it motivates me a lot. So coming back to our discussion, in nuclear physics, we know that one of the best ways to study the nucleus of an atom is by nuclear reaction, which we have discussed in detail in our previous lectures. And we have also discussed the different types of nuclear reactions, which are scattering reactions, elastic scattering and direct reactions, compound reactions, pickup reactions, and fusion reaction, exoergic reactions, and endoergic reactions, etc. And one of the very common ways of inducing nuclear reaction is to bombard incident particle onto some sort of target nucleus. In nuclear reaction, we have one projectile particle which has a property that it can be charged or it can be neutral, and we have the target nucleus on which we bombard our projectile particle, and as a result we get the residual nucleus and emitted particle. This is very common way of inducing nuclear reaction. However, you probably know that the nucleus is very tiny object, and its size is of the few femtometer, where we know that the 1 femtometer is equal to 10 raised to power minus 15 meter, which means that the majority of the space inside an atom is usually empty space. So in this kind of experiment, when incident particles are bombarded onto some sort of target nucleus, in that case majority of the incident particle usually penetrate through the empty space of the material, and only few amount of incident particles actually interact with the target nucleus inside the material and lead to some sort of nuclear reaction. Now, is it possible to calculate how many of these incident particles will actually interact with the target nucleus and lead to some sort of nuclear reaction, and how many of these incident particles will actually penetrate through the material without interacting? Okay, to do that kind of calculation, we need to understand something known as nuclear cross-section. So nuclear cross-section is the area around the nucleus on which, if incident particles are incident on it, they will definitely lead to interaction with nucleus, and all of these incident particles outside this area will penetrate through the material without interacting with the nucleus. Now my question is that what does this nuclear cross-section depends upon? The answer is that it depends upon variety of factors. First of all, it depends upon the kind of the incident particle which we have proton, it can be neutron, or it can be alpha particle. Okay, for example, if we first consider the example of a proton, you probably know that the protons are repelled by the nucleus, and because proton is positively charged and nucleus is also positively charged, so if the incident particle is proton, the protons get repelled by the nucleus and move away. So it is very difficult for us to induce a reaction between proton and nucleus because they are positively charged and repel each other. Therefore, the cross-section area corresponding to incident proton is very less. So from here we conclude that the cross-section area in the case of incident particle, which is proton, is very less. Now let's take another example of neutron. As we know that the neutron are neutral particles. If the incident particles are neutron and neutrons are charged, they are not repelled by the nucleus, and so majority of neutrons which come near the nucleus will interact with the nucleus. So the area of cross section corresponding to neutron will be greater. So here we conclude that in case of neutrons, when the projectile particle is neutron, so our cross section area will be greater. Now our nuclear cross section also depends upon energy of the particle. Let again take an example of neutron. If the velocity of the incident neutron is very high, and that neutron is much more likely to penetrate through the material without interacting with the nucleus. On the other hand, if we have a low velocity neutron or a thermal neutron, then that kind of thermal neutron will have a higher de Broglie wavelength, and it will be more likely for that particle to interact with the nucleus. So in this way we can say that our cross section depends upon the kind of incident particle, and it also depends upon the energy of incident particle. Now we feel free to define what is meant by nuclear cross section. So nuclear cross section or interaction cross section is that area around the nucleus facing the incident particle within which the incident particle will lead to an interaction with the nucleus. And I'm leaving this definition to you guys, and I want you to digest it. So we conclude from here that the greater the cross section, more is likelihood of an interaction and more is likelihood of a nuclear reaction. One more important thing about nuclear cross section is that this area can be greater than the actual size of the nucleus. It could be less than the size of the actual size of the nucleus, or it can be equal to the actual size of nucleus, and it is based upon the nuclear reaction, nature of nuclear reaction. And now my question is that if for a particular nuclear reaction, we know that the nuclear cross section of that reaction, is it possible to calculate how many of the incident particles will actually interact with nucleus? The answer is yes. Now we are going to derive that how many of the incident particles actually lead to a nuclear reaction. So first of all, let's discuss our diagram. Here we have some incident particles which are incident onto some sort of material, and we have taken the rectangular slab of that material as shown in the figure, which contains the target nucleus. And let's suppose the area of cross section facing the incident particle is A, denoted by A as shown in the figure. Let's take a very small section of the particular rectangular slab having thickness dx, and let's suppose I make a cut around distance x. So x is the distance along the direction of incident particle, and I make another cut around x plus dx. Here I want to study how many nuclear interactions happen inside this slab, and here nx is the number of incident particles which survive at a distance of x, and after penetrating through a distance dx, this quantity is going to decrease, which you easily can observe. So let's suppose after penetrating through a distance of dx, this quantity becomes nx minus dx. Here dn represents the number of interactions. Now to calculate how many interactions take place, we need to know how much target nuclei exist within this slab. Let's suppose the number density of the target nucleus within the slice is given by small n. So small n is the number of atoms per unit volume. So the number of target nucleus in dx is equal to the number density multiplied by the volume of this slice, which is the area of cross section represented by A in front of U, and multiplied by the thickness dx, such that the number of nuclei is equal to Na dx, where n is the number density, A is the area, and dx is the thickness. Now in order to find the area corresponding to this number of nuclei within which the incident particle will lead to an interaction, we multiply the number of nuclei with area of cross section corresponding to one nuclei, that is sigma, denoted by sigma, and it is equal to pi r square, such that the area of cross section is equal to Na dx sigma, where n is again the number density, A is area, dx is the thickness, and sigma is the area of cross section corresponding to one nuclei, and its value is pi r square. One more important thing about the nuclear cross section is that its unit is born, and one born is equal to 10 raised to power minus 28 meter square, or 100 femtometer. And moving on, we can say that the number of interactions divided by the total incident particle is equal to the total nuclear cross section divided by area of cross section of slab, and we denote this equation as dn divided by capital N is equal to n sigma A dx divided by A, where dn represents the number of interaction, capital N represents the total incident particles, and total nuclear cross section is represented by N sigma A dx, where capital A represents the area of cross section of slab, by where A is in the denominator and numerator, so we can cut A from upward and downward, and we simply get N sigma dx. Here dn represents the total number of interaction. If we assume that every single particle only interact once, in that case we can say that the incident particle after traveling through a distance of dx will decrease by dn. So dn can also be defined as decrease in the number of incident particles. And now we are going to use this definition of dn. We can integrate this for a certain amount of distance. We can integrate the above relation from above equation on the left hand side from n naught to n, where n naught is the number of incident particle and n is the number of particles which survive. And on the right hand side we integrate it from x is equal to 0 to x. And here negative sign is because the number of particles are decreasing, and we simply integrate it and use the property of log, such that log n divided by n naught is equal to minus n sigma x. And by taking exponential on both sides, we get n is equal to n naught e raised to power minus n sigma x. This is the required relation. This is the relation that tells us how the number of incident particles varies as they penetrate into the material medium. And we concluded from here that the resultant number of particles decreases exponentially. And we conclude this from the exponential term, which is e raised to power minus n sigma x. And this exponential decay depends upon the nuclear cross section, which is denoted by sigma. So we can say that the greater the nuclear cross section, greater is the probability of interaction, and therefore the number of particles will decrease sharply. It also depends upon the number density denoted by small n, which you can see. So in a denser medium, the decrease is going to happen sharply, and in less dense material the decrease is going to happen slowly. We can also use this above relation to calculate the rate of nuclear reaction per unit volume. So we define rate of nuclear reaction per unit volume by delta n divided by delta t, where delta n represents the change in number of particles, that is n naught minus n. And by putting the value of n into above relation, we get n naught minus n into e raised to power minus n sigma delta x divided by delta t. And in the next step, by taking n naught divided by delta t common from both terms, we get n naught divided by delta t into 1 minus e raised to power minus n sigma delta x. And here we are going to take some approximation. We approximate that our thin slice is so thin that delta x is less than 1. And if delta x is less than 1, so from exponential term we can conclude that n sigma delta x is also less than 1. And from Taylor expansion we know that if we expand some quantity by Taylor expansion, where the exponential term is very small, so we can ignore the higher order terms, and we use this definition of Taylor expansion in our case, and we get e raised to power minus n sigma delta x is equal to 1 minus n sigma delta x. So our rate of nuclear reaction becomes R is equal to n naught divided by delta t into 1 minus n sigma delta x. 1 is cancelled by 1 become cancelled by 1, and we left with R is equal to minus n naught n sigma delta x divided by delta t. Now by simplifying this expression, we define another term known as flux, where flux is the number of incident particles per unit area per unit time, and it is defined as phi is equal to n naught divided by A into delta t, where n naught is the incident particle, A is the area, and delta t is the time. So r becomes r is equal to n naught divided by a delta t into a, which is the area, into n sigma delta x. So after putting the value of n naught divided by a delta t is equal to sigma, we get sigma into a n delta x sigma. Here a and delta x represents the total number of atoms in that thin slip, and we represent it by n dash. So our a and delta x is equal to n dash, and by putting it in above relation we get r is equal to phi n dash sigma, where phi is the flux, n dash is the number of nuclei inside the thin slab, and sigma is the area of cross section. So this is another required relation. So by knowing the nuclear cross section corresponding to one nucleus, we can make calculation and know how many number of interaction will happen if particles are bombarded to material medium. And one more thing we concluded from here, that the decrease in the number of particles happen exponentially. So this was our lecture. Hope you guys like it. Thank you very much. Allah Hafiz.